go ahead and get started. Don't necessarily have everybody here yet, but I'm sure everybody will be joining in the second day back here this week. Tuesdays are always tough. It seems like Tuesdays are always a sleepy day for everybody. So in section 3.4, we're still talking about the properties of logarithmic functions. And I noticed before I left yesterday that a lot of people already had this assignment done. So that's good. That tells me that you're feeling pretty confident about the properties of logarithm and feeling pretty good about using them. So we did a little bit of the prove the properties of logarithms algebraically yesterday and use the properties of logarithms to expand and condense. Today we're going to talk about using, actually we used that change of base formula at the end even though the computer crashed this hour. I finished that up with second hour. And then today is going to be more about graphing logarithmic functions of base b, but kind of a combination of use the change of base formula and graph the logarithmic functions of base b. But this last one, we're definitely cutting, and that's the re-expressing data when seeking a model for data. I'll probably talk about that just a little bit at the end of this section, but what I'd like to do instead is, if we get through this and we have some time to spare, just do a little bit of 3.5, because 3.5 is one of those sections that can take almost 3 full days, and if we could just get a little bit of that out of the way, I think we'll be okay. And I made that decision based on the fact that I saw a lot of people had managed to finish 3.4 day 1 without a lot of trouble. Before I get started on that, I do want to tell you that for some of you, your grades on your last test reflected. I'm seeing more procrastination from folks as this goes on, this distance learning goes on. Some people are waiting and doing like 5 assignments in one sitting, and that's not good for you. That's not good for your learning. It's basically just cramming, and cramming doesn't work very well in math. So try not to procrastinate. Spend time on each of those assignments. Otherwise, what usually ends up happening is people spend so much time making up all the homework that they've missed that they don't spend enough time on the review. And you know that the review is just like the test. So I need to remind you that because this is the last test that we take in this semester, it happens the week of the last, in fact, we might be taking it. Yeah, I think we're taking it the very last day of the semester. There are no retakes. Remember, that's one of the rules that we have, is that if one of the tests lands within a week of the end of the semester, that there are no retakes. So please don't procrastinate. Do those assignments every day. And if you're having trouble with anything, email me and we can fix up a Google Meet. So let's find where we were. We were at example 6. And that starts right here, basically, where we're talking about the graphs and what we know about the graphs. But let's take a look at some basic ones before we get to that little box. So graphs of logarithmic functions with base b. Using the change of base formula, we can rewrite any logarithmic function, g of x equals logarithm base b of x, as g of x equals the natural log of x over the natural log of b. Now that's basic change of base formula there. The natural log of what it is we're trying to evaluate, which is x, divided by the natural log of the base. But what that allows us to do is say, you know what, I could rewrite this as 1 over the natural log of b times the natural log of x. And in this manner, I can talk about that graph of the natural log of x and just use this 1 over the natural log of b to describe whether or not I have a vertical stretch or a vertical compression, and use it that way. Now that's great for describing. It's not necessarily our first choice as far as graphing. And as we go through this, you'll see we don't necessarily use this for graphing. We use it to describe those transformations. So therefore, every logarithmic function is a constant multiple of the natural logarithmic function. F of x equals the natural log of x. If the base for b is greater than 1, the graph of g of x equals logarithm base b of x is a vertical stretch or shrink of the graph of f of x equals the natural log of x. And that's going to be by that factor of 1 over the natural log of b. If the base is between 0 and 1, so fraction decimal between 0 and 1, a reflection across the x-axis is required as well. And that one we'll talk a little bit more about. In fact, they have a little bit more about that on the next page, talking about that reflection. So, example 6 says we're going to be graphing logarithmic functions. Describe how to transform the graph of f of x equals the natural log of x. So this is important. They're telling us we want to talk about this as far as the transformations for that natural logarithmic function. And we want to describe how to transform that given what we see when we transform, well, change it so that we've got the change of base formula working for us. And then it says sketch the graph by hand, support your answer with a graphing calculator. Most of the time I'm not even going to bother with that. Alrighty, so we have the transformation. And the first thing they want us to do is rewrite this using that change of base formula. So the natural log of x over the natural log of 5. And then use the fact that the natural log of 5 being in the denominator means that we could rewrite this as 1 over the natural log of 5 times the natural log of x. I can see already I'm going to need a little bit more space here. All right. So now the question is 1 divided by the natural log of 5, is that a number that's a fraction between 0 and 1? So this would be a vertical compression. Or is it a number that's bigger than 1, so it's going to be a vertical stretch? So let's punch that in. And we see that's going to be a decimal, which we could convert into a fraction, possibly, between 0 and 1. So that means this is a vertical compression. So for transformation, we want to put vertical compression factor of 1 over the natural log of 5. And if you wanted to write down to 3 decimal places, that decimal that we had there, you could do that. But that's not necessary. We just needed to know this is going to be a vertical compression because that's a number between 0 and 1. So we already described the transformations. There's nothing else to this one. It's logarithm base 5 of x. But now for graphing it, there's no way I'm going to think of that as 1 over the natural log of 5 times the natural log of x. Instead, I'm going to go back to what I already know about graphing logarithms and write it as logarithm base 5 of x equals y. And I'm going to snail shell it and use it in an exponential form. So 5 to the y equals x. And then I need to put in y values in order to get x. So maybe -1, 0, 1, and 2. And 5 to the -1 is 1/5. 5 to the 0 is 1. 5 to the first is 5. And 5 to the second is 25. So I'm not using that natural log of x when I'm graphing. Instead, I'm going back to what's the easiest way to graph this function. So we have 1/5, -1, 1, 0, 1, 2, 3, 4, 5, 1, and then we need to aim at that 25 and 2. But another big part of this is us knowing that there is an asymptote for our logarithm graphs at x equals 0. So it's going to go down forever, getting closer and closer to that asymptote, but it's not going to ever touch it. And there is the graph of y equals the logarithm base 5 of x. So we described the transformations, and we graphed it, and we can move on. Over here to B. h of x equals logarithm base 1/4 of x. Now, with this one, I want to talk to you a little bit about what they said as far as, okay, if your base is a fraction between 0 and 1, just use a reflection for that instead. So here's what they're doing. They're saying if we wrote this as y equals logarithm base 1/4 of x, and we snail shelled it. So 1/4 to the y equals x. And then we said, you know what? We want to use a base of 4 right here. We don't want to use a base of 1/4. Well, we could do that by changing that to 4 to the negative 1. So we would get 4 to the negative y equals x. And then, if we wanted to put it back in logarithm form, we would take the logarithm base 4 of both sides, because over here our inverses would be gone, and we would get negative y equals logarithm base 4 of x. But of course we wouldn't leave the negative there, because we know we always have things y equals when we're graphing. So we would multiply both sides by negative 1 or divide both sides by negative 1. It doesn't make any difference. And get y equals negative logarithm base 4 of x. Now, when you think about it, we could have put another variable here for 4. It could have been a z, and this would work for any fractions that have the 1 on top of a number. And so they're saying instead of thinking about this as a fraction base, what we generally do is change it to just a normal integer base. In this case, we're using whole numbers for bases. And what we would do is just think, let's have that be a reflection instead, and not worry about the fact that that was a base of 1/4. So that's one of the things that we need to look at today, is whether or not that's worth all of that effort. And our transformations for this one, again, are supposed to come from natural log. So h of x equals natural log of x divided by natural log of 1/4, and that would be h of x equals 1 over the natural log of 1/4 and natural log of x. So then we need to figure out, well, what is that 1 over the natural log of 1/4 going to do? Well, again, we could rewrite it as 1 over the natural log of 4 to the negative 1, and realize, well, with powers, exponents are supposed to come out in front and become multiplications. So h of x will equal negative 1 over the natural log of 4 times the natural log of x. So for transformations, we would want to talk about that reflection, and we want to know what 1 divided by the natural log of 4 is. So let's take a look at that. Again, not a surprise there that that's going to be a decimal between 0 and 1. So we also have a vertical compression. So that negative gives us the reflection, which I have run out of space for my transformation. So I'm just going to write that down here. Transformation is a reflection over the x-axis and a pardon me, vertical compression factor of 1 over the natural log of 4. So two little pieces here. So with this one, we've got a lot to describe, a lot to figure out about what's going on, because that base was a fraction between 0 and 1. But to graph it, we don't have to do all of that. It's totally up to you how you want to attack this one. But I would go back to what we were doing in A, where we said, let's just go back to the original, where we have y equals logarithm base 1/4 of x. and snail shell that. So it'll become 1/4 to the y equals x. Now, again, totally up to you if you want to write this 4 to the -1 and get the negatives in there. But I think I'm just going to work with it as it is. And remember that I'm putting in y's here. So I need a few more negatives this time because it is a fraction between 0 and 1. To the -2 power, we'll take the reciprocal and then square it. That's going to be 16. And to the -1 power will be the reciprocal, and we'll just flip it. That's going to be 4. To the 0 power is 1, and to the first power is 1/4. And then we'll be able to graph this. So 4, -1, 1, 0. And then we have 1/4, 1. And again, we still have our asymptote of x equals 0. So I start to think about what's going to affect that asymptote. If I translate this left, right, up, and down, which one of those is going to affect, or which two of those are going to affect that asymptote? And I realize it's a left and right movement that would change that. So in our formula that uses A, H, and K, it's going to be the H that would give me a new asymptote. Now, I'm pretty sure these little boxes just have, they're just showing the transformations that take place from the natural log of x. But when we're graphing, so much easier to just go back to the original and use the snail shell to write that exponentially, and everything will be just fine. All right. Now, here's the big box of generalizations. So, we can generalize example 6b in the following way. And it says if the base is greater than 1, then 0 is less than 1 over b, which is less than 1. And it could be rewritten, instead of having a fraction base, as just a reflection over the x-axis. And for more complicated examples, that is absolutely a good idea. You absolutely should do that for more complicated examples. And that's where we're going, so we want to think about that in advance. So when given a function like h of x equals the logarithm base 1/4 of x with a base between 0 and 1, we can immediately rewrite it as h of x equals negative logarithm base 4 of x. Because we can so readily change the base of logarithms with bases between 0 and 1, such logarithms are rarely encountered or used. Instead, we work with logarithms that have bases greater than 1, which behave much like natural and common logarithms, as we now summarize. At the beginning of the chapter, they said, for our purposes, assume that our bases are going to be greater than 1. Well, that's what they're talking about here, is that we could always rewrite these as reflection so that we don't have to have a base that's a fraction. And this, of course, needs a couple of arrows. So here's our big box of logarithmic functions. F of x equals logarithm base b of x with b greater than 1. And our domain has that asymptote to think about at x equals 0. So notice our domain is from 0 to infinity, not including the 0. Range is all reals. This is going down and up forever. This is definitely a continuous graph. It is also increasing over its entire domain. There isn't any symmetry, and it's not bounded above or below. There's no local maxes and mins, and there's no horizontal asymptotes. So there's a whole lot of stuff we can put no and none for logarithmic functions. But our vertical asymptote, really important that we know that that's a vertical asymptote. This graph does not stop. Even though our graphing calculator does not show the arrows, it does not stop. And our end behavior, look at this. There's only one. Well, this graph does not go left and right forever. This graph only goes to the right forever. And so we only have one end behavior for these graphs. Remember, there's a cutoff here at x equals 0, so it's not going to the left forever. And so we just look at, as we go to the right forever, this graph is going to positive infinity because it's going up. So there's our nice little box of a summary for logarithmic graphs. And we've got a couple extra examples, and like I mentioned, we're starting to see a little bit more happening with them. Sketch the following functions. Show the asymptote, y-intercept, find the domain and range, then determine any end behavior. So when we're graphing and there's more A, H, and K going on, it really is a good idea to think about all of those transformations before you get started. So with f of x equals negative logarithm base 3 of x plus 1, we would start with a parent function of y equals logarithm base 3 of x. So you have to think, well, what changes did they make here? And we have a negative in front of that. So that's going to be reflect over the x-axis. And then we think about the fact that the x by parentheses is attached to that plus 1, and x is always the opposite of what we think it should be. So that's actually going to translate 1 unit to the left. And that's really important because that changes my asymptote. My asymptote is not at 0 anymore. My asymptote is now at x equals negative 1. So that's a big deal. Now the second thing that they have us do is find the y-intercept. Where is this going to cross the y-axis? And to do that, what we have to do is put a 0 in for x and see what we would get. So if we put a 0 up here, 0 plus 1 is 1, and this is going to say the negative logarithm base 3 of 1. So I think about what's going to happen here, and I realize, well, logarithm base 3 of 1, if I snail shell this, 3 to the something is 1. Well, that something is 0, and a negative of 0 is still going to be 0, so my y-intercept is at 0, 0. So I know a point that's definitely going to be on my graph at 0, 0. The domain. Well, that was why it was important that we figured out what was going on with our asymptote here, because our asymptote is now going to be 1 to the left. That's going to be from negative 1 to infinity. Then I have to think range. Well, it's still going to go up and down forever. But I probably want to see the graph before I start talking about the end behavior. So I make my little table. And remember, my parent was going to be y equals the logarithm base 3 of x. So I snail shell that, kind of backwards, a lefty snail shell here. 3 to the y equals x. And I put in some good numbers, negative 1, 0, 1, 2. Now how do I know those are good numbers? Because I remember I'm graphing on a negative 10 to 10 scale here, and 3 squared is 9, and then I'm already going to be off of my grid. So negative 1 power would be 1/3. 0 power is 1. First power is 3. Second power is 9. And then we had to do a reflection over the x-axis. And what a reflection over the x-axis does is it makes all of the y's negative. So I can take all of those y's that I had and make those negative, and make this kind of a little three-parter here for that reflection piece. Now, I want that to be my shape graph that I have on here. So my shape for this is going to be 1/3 1, 1 0, 3 negative 1, and 9 negative 2. And don't worry about that 0, 0. That's all going to work out in the end. So here is the parent function. But remember, we have to translate this, and we have to translate it 1 unit to the left. So that's where that 0, 0 comes into play, because we're going to move this all 1 unit to the left. And again, approaching that asymptote, but not crossing it. So let's see if we did everything they asked. Sketch, well, we actually did graph. We didn't sketch. Show the asymptote, got it on there. Y-intercept, yep. Domain, range. Only thing we have left is the end behavior. So this one is not going to the left forever. So we'll do the limit as x approaches positive infinity for f of x equals, and because of that reflection, this one is going down. So negative infinity. And now we have it all done. So more to keep track of. In fact, as you look at B, you see, gosh, this one's going to have even more stuff to keep track of for little g of x here. And the first thing I think is, well, that's not in the right format. Because typically we have our little a in the front, and then we have logarithm base b of the quantity x minus h plus k. So that 2 is not in the right place. And I'm going to rewrite logarithm base 0.5 as logarithm base 1/2. All right, so there's a good start. A good start is getting the logarithm in front and getting the plus 2 in the back, that translation in the back. Then I remember, wait a second, they said I don't have to use those fractions for bases. I could use a reflection instead. So g of x will equal the negative logarithm base 2. That'll be nice. Oh, everything in those parentheses is backwards, and it's going to have a negative in front of it. So we would want to factor out a negative and reverse it so that we can see all the transformations that are going to take place here. All right, so let's talk about those transformations. This one in the front is a reflection over the x-axis. Now, as we move from left to right, the next thing we hit is a negative in front of the x. That's another reflection. So that's a reflect over the y-axis. So we're going to flip it, and then we're going to flip it again. And then x minus 3 would give us translate to the right. Three units. And the plus 2 in the back would be 2 up. So 2 units up. So we're reflecting over the x-axis, reflecting over the y-axis, translating to the right 3 units, and 2 units up. So again, this one needs a parent, and the parent is going to have all those reflections in it, and then we'll just translate it. So next thing to think about would be, well, let's put that asymptote on there before we get going too far. And since we had this x minus 3, we knew that we were going to have a new asymptote 3 units to the right, which will be x equals 3. Now the y-intercept with this one is not as nice and easy, because we really need to put it back into the original. So we've got 3 minus 0. So we're going to need to punch in, using the change of base formula, the logarithm of 3 divided by the logarithm of 1/2, and we can use natural logs for that. And then we'll add 2. So 0.415 to 3 decimal places. Remember, that's not going to be in our original shape graph. That's actually the y-intercept of the final answer. Domain, Well, let's take a look at that once we get all these reflections taken care of. And you could do it now if you wanted to, but usually it's helpful for people to see the graph and make sure that everything's looking the way it is. Range we know is going to be negative infinity to infinity, but let's get going on the graph so we can feel a little bit better about this. So first things first, what we want to do is think about the fact that we had this base of 2, and then we made reflections to that. So if we have logarithm base 2 of x equals y, we'll get 2 to the y equals x. Put in some appropriate y values. And this time I'd go up to 3 because 2 cubed is 8. And like I said, we're going negative 10 to 10 here. To the negative 1 power is 1/2. To the 0 power is 1. To the first power is 2. To the second power is 4. And to the third power is 8. But this one had us reflecting over both the x and the y axis. So that means I need to make my x's negative, and I need to make my y's negative in order to get that shape on there. So negative 1/2, negative 1, negative 2, negative 4, negative 8, and positive 1, 0, negative 1, negative 2, negative 3. So that's going to be my shape, which takes care of my reflections. And then I can just translate it once I get that done. So you use the first column and the last. Negative 1/2, 1. Negative 1, 0. Negative 2, negative 2. And negative 8, negative 3. So I think is about there. Now, again, that would be with a normal asymptote of x equals 0. But we have to move this one. So we need to move this 3 to the right and 2 up. So there's our new graph. And I think seeing it helps people figure out the domain piece here, which is, oh, this is going to come in from negative infinity, and it's going to approach that 3, but it's never going to get there. But yes, we're still going up and down forever. Again, we don't get both end behaviors. This one is going to go to the left forever. So the limit as x approaches negative infinity, and this one was g of x, and it is going down as we go to the left forever. So logarithms, a little more involved, and it definitely helps to use your table a little bit more with logarithms, and then just keep your translations for your second graph, your solid graph, the one that we have done. So we've done everything again with this one, and in fact, it said sketch, and we made a graph, just as we would if we were taking a test. Made sure that we changed this base of 0.5 into a base of 2 by adding an additional reflection. So, like I said, a lot to keep track of with logarithm graphs. Now, let's just say that we don't have to do the whole thing. Let's say that we just want to know what the domain of these functions would be. Well, what we have to do is remember that domain comes from the x's. So, what I have to do is I have to make sure that this is greater than 0. And that's because when we have our positive bases, you can't raise something to a power and make it 0. So we need it to be positive. Now, we'd solve this with normal algebra and say add 16 to both sides, take the square root. But this one, because it was x squared, we have to be sure that we maintain the fact that we have a positive x value. And so this takes us quite a ways back, because if we have absolute value and it has to be greater than 4, then we have to remember that that means x could be less than -4 or x could be greater than 4. And we use that for our domain. So domain of f is going to be from -infinity to -4. And that's in union with 4 to infinity. So that one, we could do that algebraically and we wouldn't have too much trouble. But if you really wanted to, you could say, all right, I just need to find out where x squared minus 16 is going to be greater than 0. So I could graph that. And we might not even have to graph it, because we've done so much with quadratics that maybe you're already thinking, oh, I know exactly what that's going to look like. It's going to be my parabola, but it's going to have a vertex down there at 0, -16. So if we graph it, we shouldn't be surprised to see that where it's greater than 0 is here and here. And so we describe that with the x's as -infinity to -4 and 4 to infinity. So we can use graphically if we need to for the domains, which brings us to the next one, which it's a little more complicated. So usually students like to see this one graphically. So I'm looking at 4 minus the square root of x. And right away I realize, well, x is going to have to be greater than or equal to 0. Now, can it be 0? Let's see. If I put a 0 in here for x, that's going to be 4 minus 0. Yes, that's still positive. So it can be 0 in this case. But overall, four minus the square root of x has to be greater than 0. So we could add the square root of x to both sides, square both sides, and we see that x is going to have to be greater than or equal to 0, but it also has to be, if we reverse this, less than 16. So our domain for g is going to be from 0 to 16, inclusive of the 0. Now, here's why I said this one, it does really help to see it graphically. So let's graph 4 minus the square root of x. And we can see from 0, we're not out to 16 yet. We could change our window here. That's the portion of the graph that's going to be above the x-axis. So we can use it graphically as well. And these two examples were just to kind of finish up what, I don't know, might be considered, I guess, the toughest part of logarithm graphs, which is figuring out that domain piece. But most of the time, if you can get a look at it and see what the graph is doing, then you're going to be fine anyway. So whether or not you can figure it out algebraically or you can do it graphically, the last test that we take, the Chapter 3 test that we take, is bound to have, a lot more multiple choice on it than we've had in the past, because we have to turn around and get those grades back into the school pretty doggone quickly. So however you can do it, just make sure that you've got a way that works really well for you. Now, because we have 9 minutes left, I'm going to do just a teeny bit, if my computer allows me to have this other file open. Just a teeny bit of 3-5, not much at all. So this is equation solving and modeling, and of course we're talking about logarithms and exponents here. Be able to review solving exponential equations algebraically and graphically, and solving logarithmic equations algebraically and graphically. We'll talk about the rest of these tomorrow. What I want to do is just finish up a couple of problems that were basic for you even last year in Algebra 2. So we've got equation solving and modeling, and for any exponential function, if we have this base of b, and we know that b to the u has to equal b to the v, the only way that's going to happen is if u equals v. b is already the same. We need those exponents to match. And for any logarithmic function, if the logarithm base b of u is supposed to equal the logarithm base b of v, well, u has to equal v. That's the only way it works. So we have a lot of methods that we can use to solve exponential equations. And the first one is get common bases. And that's the one I want to go over with you with just two little problems here before we stop for the day. Solve the exponential equations algebraically. And the method is getting common bases. So 9 and 27 are my bases right now. And those are not the same. They're not common. So I have to think of a smaller base that I could use for 9 and 27, and that would be 3. So 9 can be rewritten as 3 squared to the 2x, and 27 can be written as 3 cubed to the x minus 1. And then we know that when you raise a power to a power, you're supposed to multiply. So this would be 3 to the 4x equals 3 to the 3x minus 3. And now here's that kind of duh moment that they talked about in the beginning of this. If you already have bases of 3, well, we don't need those anymore. We need 4x to equal 3x minus 3. That's what we need. And if you subtract 3x from both sides, you've got it. So x has to equal negative 3. That's the only way this is going to work. Now I get to b, and I think about what I did in a, and I realize, well, I don't want that 20 there. You know, that's messing up the works. I better divide both sides by 20 first. So this will say 1/2 to the x over 3 equals 1/4. Oh, wait a second. 1/2 and 1/4, those are both bases of 2. This is 2 to the negative 1. And this is 2 to the negative 2. And again, when you raise a power to a power, you multiply. Well, if this is going to be true, these big 2's don't matter. They're already the same. I need negative x over 3 to equal negative 2. And we could slap a 1 underneath this, and we could do a little cross multiplying. So negative x times 1 will give us negative x, and 3 times negative 2, negative 6. We divide both sides by negative 1, and we get x equals 6. So like I said, I didn't want to do a lot with this today, but I just wanted to get a little bit of a head start, so maybe we're not packing so much in the next couple of days. All right, and I promised to talk to you about when we use the fact that we've got a model and we re-express the data. Most of the time this is going to be in science class. Anytime that you have really big numbers or really small numbers with a lot of zeros, we tend to use logarithms to re-express that data because it takes a lot of those zeros out as you use logarithms. So that's the one. Again, we're cutting it out. You'll get it in science class if you really need it in science class, that re-expression of data. But come here, let me move it. There we go. That was 3-4 day 2. So we finished up that graphing, and you'll do page 289, 33 to 37, 39 to 53, and, oh, yep, this is where we scrapped the re-expression of data. So you won't need those. You just need 33 to 37 and 39 to 53, and that'll take care of it. So have a good day, everybody.